to think about what would happen if I applied a dagger yet again, I want to think a little bit now more in general terms. We've actually gotten all the pieces of algebra in place. So I think we're ready now to try this in general, right? So let's just imagine the general case. So in general, right, let's say I know what the nth excited state is, right? So I know then I've proved, let's assume, it's going to be a little bit like a proof by induction. I'm going to assume that I've got the nth state in general, right? We're going to assume this, right? The question is going to be, right, is in fact the next excited state. Can I get that by simply applying this operator, this a dagger operator, onto phi n? Is that a pure state? And along the way to answering this, we will also, of course, find out what that next energy level will be. So the basic way to do this, to find out what we get, is we're going to try again. H hat now applied to our guess at phi n plus 1. And what we're hoping to get back then is just some constant, which would be the next energy level, times my original state. But we have to prove that. I'm not going to just go ahead and assume that. So we follow the same pattern as before. We now have all the algebraic pieces in place. The Hamiltonian is a dagger a plus 1/2. My guess for that next excited state, the thing I'm working with, is applying a hat dagger to phi n. And now we can once again expand this out. It'll be a hat dagger, a hat, applied to the result of a hat dagger on phi n, plus 1/2 of a hat dagger applied to phi n. Once again, I like this term because that's just a constant times really what I'm starting with, right? I'm starting with, again, this state here. So just to emphasize that, let me write it down here again. A dagger on phi n, right? And this term, once again, should be something that I like, but it's not quite in the form I was hoping to find, right? So once again, I can play my game of commutating these two, or commuting these two, we say. So let's put in that commutator. I've now disturbed, if you will, the order in the universe. I've just violated my equality here, but I can quickly restore it by adding things back in the properly commutated order. I mean, the commutated order that then restores things. And now we can look a bit at what we've generated. The first thing that I would like for you to notice is that, once again, this we recognize as just the identity. Right? So I've got two terms here that are just a daggers, right? This is two terms that are really what I had started with, a dagger phi n. That's nice. This term maybe looks a little bit different at first, but if we think a little bit about it, a dagger a on phi n, this looks like something like the Hamiltonian actually applied to phi n. So it looks like we should be able to do something really with that term. Another way of thinking about this is to try to group things in a clever way. If we look at all the terms that we have, they all start with an a hat dagger, and they all end with a phi n. So let's write it down in that form. So let's start everybody off with an a hat dagger, a nice big parentheses for whatever goes on the inside, and a phi n on the outside. And then what goes here on the inside, we have a 1 coming from the first term. That's clear because that gives me a dagger phi n. The next term has a 1/2. I'm going to write it over here for reasons that you will see in just a moment. That's a 1/2 a dagger phi n. And then finally this term, the a dagger and the phi n's are accounted, but I have this extra piece on the inside, plus a hat dagger a hat. And I hope you can see something very exciting here, because this term is most definitely something we recognize. This is actually the Hamiltonian. And I'm very excited about having the Hamiltonian there because I know what the result is of applying the Hamiltonian to any state. So let's incorporate that fact. So I have A hat dagger 1 plus, and of course all this is acting on phi n. So I've got my 1 plus phi n here, but when I apply my Hamiltonian to phi n, I just get En times phi n. So I can write my En here. Finally, notice this thing, right, is just a constant. That will most definitely just commute with this operator, which is just derivatives and multiplying by x. And I can, of course, always pull a constant out through all of those types of things. So let me rewrite it then in a more suggestive form. This is En plus 1. That's how I'm going to write that term. What's left here is A hat dagger phi n. And the beauty is I've applied a h hat to A dagger phi n, and what I've gotten back is a constant times what I started with. Now, the A dagger phi n, the other code name we had for that was just phi n plus 1. So I've just proved that my h on my proposed phi n plus 1 is indeed nothing other than a constant times my original phi n plus 1. So it is definitely a pure state. And the second thing that we've proved is that the energy of this next state, En plus 1, right? E sub n plus 1, the energy of this next state is nothing other than the energy of the preceding state plus 1. So that tells me then that every time I create a new state, I'm just adding 1 unit of energy into the system. So therefore, phi n plus 1 is a pure state, Very good. Right? That works. And I should write it this way. Phi n plus 1, defined as just applying this dagger operator to phi n, is a pure state. And the other thing we learn is that the energy of any of my states is of the nth state would be the energy of the 0 state, which we already decided was 1/2, plus however many steps we've gone up. So it's 1/2 plus n, or it's usually written actually as n plus 1/2. And these are super key results because then that shows us how we can construct the various solutions to the time-independent Schrödinger equation and produce all of the excited states of the harmonic oscillator. And that then really concludes the lecture portion of our analysis of the harmonic oscillator. There will be additional pieces that we will explore on, of course, the assignments and the problem sets.